All right, today we're going to begin looking at waves. This is our first video, so it's just a brief introduction. We're going to talk about three basic types of waves. There are obviously more than that, but we're going to look at transverse waves, compression waves, and electromagnetic waves, and a couple things they do. Basically, wave parts, speed, reflection, refraction, and diffraction. It's pretty important. But for now, let's define waves. It is an energetic disturbance that moves through a medium. So basically, a wave is moving energy. There are two basic types of waves that we're going to deal with. One is mechanical waves. The other is electromagnetic. And the big features of this, this moves through and disturbs a medium. And for a mechanical wave, our classification for transverse and compression is going to depend on how it disturbs the medium. But the important thing is here, the medium I can't spell zero. The medium has zero displacement. It's moved and then it moves back to where it was. That's what's going on with a mechanical wave. An electromagnetic wave, and what we really mean by this is light, and that encompasses everything from radio waves to visible light to microwaves to gamma rays. With an electromagnetic wave, it's just energy moving through a medium, and this has photons, and it's just different. So we will talk about light as we go through these wave properties, and it shares a lot of similarities to mechanical waves, but the way it moves and the way it affects the medium is a lot different than mechanical waves. So we're gonna keep these two separate, but we will look at their similarities, and then the last part of this chapter will be devoted to light, and we'll get more in depth with how it works. Right now we're concerned with mechanical waves. So let's jump into that. And again, we're going to keep in mind that a wave is the energetic disturbance that moves through a medium. So a transverse wave, in this case, the medium is displaced perpendicular to the wave velocity. Basically, what we see happen here is everything you know and love a wave to be. This is where we have the crest and the trough, and it's a basic wave, sine and cosine wave shape. We see this in strings. That's what we're going to look at it mostly with. And the medium, the string, the spring moves up and down while the velocity of the wave is forward. A little video of it, but this is what you see on a string. This is what you see with sort of an earthquake wave, and not that water's strictly a transverse wave, but this is kind of what you think of when you see a water wave moving. Okay, this is a simple, very simple demonstration of a transverse wave. Here are my particles of my medium. We're going to see the wave come in, and the wave is going to move this way. What I want you to pay attention to is how the particles in the medium move. Look especially at this little red one. Here's a little video of that. The next thing we have is a compression wave. Another way that we talk about this is a longitudinal wave. With this is like sound. We're pressing into a medium and moving back, and we have this compression moving. That's what's carrying the energy. And so for a compression wave, the medium is displaced with the velocity. So, and the illustration is going to do us a much better job here, and we'll talk about it a lot with that. But essentially, the medium is going to move back and forth while the wave moves forward. And so, all right, here we have a little demonstration of how sound waves work. This is a great analog for what happens with sound. You have something that shakes, right, and that's going to push particles together. And what we see is this push traveling all the way through. But an individual particle, so if you were to look at an individual particle right here, you'd see it moving back and forth. The individual particle is just moving side to side, but this push is what's moving through here. Now, if we look at these things, what we see is a compressed area, that push that's traveling, that's like a crest, and then we see this area right here, which is not as compressed. We call that a rarefaction. So here's a video that's going to help us see that a little bit. Now, an electromagnetic wave, again, is different, but what's notable about it is that electromagnetic wave doesn't need a medium. This is how we get light from the sun. In fact, stuff gets in the way. Electromagnetic waves can travel in a vacuum. Compression waves and transverse waves cannot. They must have stuff to move. And electromagnetic waves don't. They are completely independent of not completely independent, but they can move without a medium. So let's look real quick at wave parts. This is not a picture of a compression wave. This is what a transverse wave looks like, and we've seen this before. So the y-axis is displacement, the x-axis is distance. In math, you looked at this as displacement and time, and you talked about period and frequency and all that stuff. This is just for distances. So if my medium is displaced upward, the amount of that upward displacement is the amplitude, and then the wavelength, it's kind of a bad picture, it goes from here all the way over to here. It's the length of one complete cycle. And we use lambda for wavelength. It's a Greek symbol. It's lowercase lambda. So, those are our basic wave parts. Now, the amplitude here has to do with the energy of a wave. The more energy you put into the wave, the bigger the amplitude goes, but that's not necessarily going to affect anything else. So, some things that you've talked about before are frequency and period. So the frequency of a wave, we use an F for that because it makes good sense. The frequency of a wave has to do with number of waves per second. And that's measured in 1/seconds, or what's called a hertz. And basically, frequency is a very good description of it. It tells you how often that wave comes in a second. Period is the inverse of the frequency. We use a T for that. I think it's a Latin thing. Period tells me number of seconds per wave, and for the period, it's just telling you how long it takes for one complete wavelength to pass you by. It's measured in seconds because it's the number of seconds per wave. Now, our relationship between frequency and period is inverse. If I take and flip the number of seconds per wave, that's going to tell me how many waves go by per second. Now, this is going to help us get the velocity of a wave. Velocity, we know, is displacement over time. So for this wave, for one wavelength to go by, the displacement is that wavelength, and the time to do that is a period. Now, we don't usually say lambda over t t. Usually the way we write it is that the velocity is equal to the frequency times the wavelength. I think in chemistry last year you used a nu for it. That's all right. But frequency times the wavelength gives me the velocity. And we're going to actually look at what all of that means. But parts of a wave is simple. So velocity is sort of a cool thing. What we say about velocity is that it only depends on the medium. And I'll use sound to talk about it. So let's talk more about wave velocity. Here's a little formula. Velocity is frequency times wavelength, but it only depends on the medium that the wave is traveling through. So I could have waves of multiple frequency, okay, but that's not going to affect how fast the wave goes through the medium. When we look at frequency and we look at period, these are properties of the wave source, okay? Properties of the wave source. If we're talking about sound, it's the speaker that pushes the air. Remember that illustration of our compression wave? Well, the frequency of the compression wave has to do with how often that thing is pushing the air. That's not going to affect the velocity. How quickly that disturbance moves through only depends on the medium. So even though this equation is written as if velocity depended on frequency and wavelength, velocity depends on nothing other than the medium. I can have multiple different frequencies of sound moving through the air at the same time, moving at the same speed. That's why when all 17 or 18 or 35 of you in class talk at the same time, even though your voices have different pitches, different frequencies, they all get to my ear at the same time. Someone with a low voice doesn't end up having slower sound coming out of their mouth. It all works at the same time. Because air, the thing that the sound is traveling through, the medium, only has a certain set speed for sound to move through it. Same thing with the spring waves that we're going to play with in class tomorrow. Looking at that, a wave can only move through that at a certain speed. It doesn't matter how hard you snap the spring to make it move. It's going to go at that speed unless I somehow change the medium. And so really what we need to write down is the only way to change wave speed is to change the medium. Okay, that's the only thing that the velocity of the wave depends on. Frequency and period are properties of the wave source. Wavelength, actually, this depends on velocity. A better way to say this actually would be that lambda is equal to our velocity divided by the frequency. If the velocity of the wave goes up, lambda goes up. So if I go into a medium where we have a faster speed for my wave, it's going to have a longer wavelength. Because the medium does not affect the frequency. The medium affects the velocity and the medium affects the wavelength. Frequency only has to do with the source. But if I change the frequency somehow, like if I make the frequency, let's do another color for this. If I make the frequency go up, that means I have more waves per second, but they have to have the same velocity so that lambda, in fact, will go down. They're inversely proportional. So, these things depend on the source. This depends on the medium and velocity. Velocity depends on the medium. But for a given medium, the velocity has to stay exactly the same. Light is going to move at the same speed through empty space, regardless of whether it's visible light or whether it's some type of radiation or a radio wave. It all moves at the same speed. The important thing to remember, again, is the only way to change wave speed is to somehow change the medium. Think of a stringed instrument. In that case, you have a string. Right? That's where our wave's going to be. It has a set wavelength, and what we're going to do is adjust the tightness, change the medium to change the velocity, and adjust the frequency. This comes out a lot. Hopefully we'll have time to talk about a bunch of examples with wave speed. Now, there are some properties we need to look at. Refraction, diffraction, and reflection. Now, going off of our idea with wave speed, these are all ways to bend waves. Refraction is bending as a wave changes medium. So what's happening is that the wave is changing medium, which also means it's changing speed. And so what we see here is light moving fast with a big wavelength. And as it changes medium, the speed changes. Okay, it slows down a little bit. I get a smaller wavelength, and because of that, it turns a little bit. This is sort of a picture of all the crests lined up. But my wave would be moving in this direction, and then when it hits the water, when it changes medium, it turns a little bit. That's a terrible picture of it, but it goes from moving this way to moving more this way, and it bends as it changes medium. That's refraction. We see this mostly with light. And when we talk about light toward the end, we'll talk about refraction a good bit. With light refraction, this is how lenses work, which is a big deal with me with the glasses. We don't really talk about refraction a lot when we talk about sound. It's not something that we see a lot of with sound. But it's the bending of a wave as we change medium. And so we'll talk about any type of changing medium as a refraction type of process. So diffraction here is the bending of a wave. We'll go back to green. As a wave moves through a barrier, or around an object. So, basically with diffraction, you have your waves moving in this direction, straight towards an opening. And as these waves press through the opening, they spread out. So part of the wave still goes straight, but it sort of bends and changes its shape. Now, the speed is the same on one side of the barrier as it is on the other. The wavelength is the same. The only thing that's different is the direction that it's changing in, because it's squeezing through this opening to go through. A good example of diffraction is sound being able to go around corners. A lot of that has to do with reflection, but a lot of that has to do with the sounds that we make pressing themselves through openings, so that if I'm yelling at someone in class and you're standing outside in the hallway through the open door, you can hear me because that wave is bending as it goes through the door. That's diffraction, bending as it moves through an opening. Sound bends through a door because they're about the same size. Light doesn't do that so much because it's tiny, and we'll talk about that a little bit more as we get into diffraction. We're just hitting the basics. And then reflection, well, for sound that's an echo, and for light that's a reflection. There's no other way to put that. This is what happens with mirrors. It's the bouncing off, it's the bouncing of a wave off of a barrier. In reflection, a light wave comes in from an object, hits the mirror, and bounces off perfectly and gets to your eye, and you see the image somewhere behind the lens. We'll talk about this a little bit with light, we'll talk about this a little bit with sound, and we'll talk about this a little bit with strings. These are the basic wave properties that we'll look at, and we'll mention them as we can, as we talk about strings, sound, and light. So, this is our introduction to waves. Thanks for watching.